All right, we're about to start our very first workshop with Dr. Anderson, and it's going to be an intro to R. I am Neha. Me and Kevin formed the education committee along with Amanda, who is currently on time off. She's on maternity leave, so you'll see her in a little bit in February, and we're ready to kickstart this program. I'm gonna let Kevin introduce Steve, okay?
Sure. Yeah, we're very happy to have you here. We're also happy to have Dr. Steven Anderson here with us today. Steve is a postdoc at the University of Florida. He works with Dr. Brian Pearson's lab in the Department of Environmental Horticulture, leading the Controlled Environment Essential Oil Hemp Research and Germplasm Curation Project. So Steve recently graduated from Texas A&M, where he did his PhD in quantitative genetics and maize breeding, and that was under the guidance of Dr. Seth Murray. His research goals are to improve agriculture productivity, sustainability, and quality through applications of best management practices, quantitative genetics approaches, statistical modeling, remote sensing, and applied plant breeding. And just to further introduce Steve and just to kind of highlight some of his work, and Steve and I have known each other for a few years now. We always see each other at conferences and mainly at conferences or symposiums or things like that. And here's one of his papers that came out of his PhD, in which he was predicting maize yield based on drone imagery. So I thought that was very, very exciting, enlightening, and a great, fantastic paper. So I'll put the link to this paper in the chat, and also I'll probably put the link to his one of his previous webinars on remote sensing in the chat as well, if you're interested in more of what Dr. Anderson's doing. But without further ado, I'd like to pass the ball back to Steve. And Steve, why don't you take it away? Thank you for coming, and you go for it.
Thanks, Kevin. Okay, so let me get my screen going here. Oh, you gotta give me the ability to share.
Can you request it and I'll let you?
I can't even request. It just says host disabled participants.
I'll make you the host. How about that?
Okay, yeah, and I can send it back as soon as I...
I have a request from everybody. Please mute your microphones and type any questions you have in the chat message box. That way, one of our panelists, if not Steve, while he's presenting, will still be able to answer your questions. If you have something burning that just absolutely needs attention, raise hand and Steve will take care of it, okay?
Okay. Should be able to see my screen now over here, the R Studio. Okay, so before we begin, I just want to show everyone should have RStudio open, and below in this bottom left corner, it should say the version of R that's loaded. It doesn't really matter which version you have. I always recommend you have the highest version, but if you have a different version than me, don't worry, it should be fine. So we're going to start, and then the next thing is if you have that text file that was in the email, you can go into File and open it as open file here, and you should be able to open that text file like this, and it should open up in the top left corner. If you don't have that, let's make sure that no one is missing this file first, because this is the entirety of the workshop today, and it's kind of critical that everyone has it. Let me give everybody like a minute. Okay, so a quick little trick. If you, as you saw when I loaded it in, it comes in all white, but you see on my screen I have all these different colors. So RStudio is really nice because the global environment will allow you to do this. If you want to see the colors, you're going to have to copy the entire script, and then open a new file. And if you paste it in there, you should see the colors. It'll let me paste. Okay. So That's just a little trick if you want to get the different colors. I like having the different colors. It makes reading script a lot easier and seeing what you're doing. So let's just talk about this environment really quick here. So if you were running a normal R, just the base R, you would only see what's called the console, which is down here, and this is where things are actually happening in R. But what we have in Studio is in base R, these other screens will either be hidden. For example, the environment screen, you usually never see that, and you have to call it, and we'll talk about how you can call those things. And the script you usually have to have as a notepad, and you have to copy and paste it over into the console. So in our Studio, it's really nice because we can simply write things right above here and alter our script as we see that we want to make changes. And then we can execute them straight down into the console. We don't have to copy and paste all the time. And then this bottom right area, there's a lot of things here. Your working directory under the Files tab, and we will talk about that in a few minutes. There's the plot screen where if we're making graphs, we can see those quickly. This will pop up in base R as well. And then we have a lot of packages that we can easily just graphically user interface click and load them in. We'll talk a lot about the help screen today. So there's a lot of functionality within this R Studio. That's why I highly recommend, especially beginners, to use it to build your scripts. And if you want to move on to terminal-based R, where you just run like a batch script or something, you can do that after you have learned how to write scripts efficiently. Okay. So a few other things about R Studio. Okay, yeah, so let me show you that really quick. I see that in the chat. So
Steve, are you recording? I don't think you're recording or.
I'm
Yeah.
recording. It's
Okay.
recording on my end.
Oh, it is? It didn't. Oh, yeah, it is recording. Okay, sorry.
Okay, no problem. Okay, yeah, sorry about the the GitHub can be a little finicky sometimes, and I'll show you how to. Okay, so if you're at the script, you can't actually download the script in GitHub. You have to copy it. And the way you copy it is you go. Where is it at? There was a button yesterday. Where did it go?
I will email it to him in a second.
Okay. So anyways, you could essentially just highlight the whole thing like this, right? And bring it in, right? You can copy it and then bring it into your new script and bring the whole thing in, and then you'll have it. Yeah, sorry, unless you send things into GitHub a specific way, downloading is not easy. Because GitHub, you usually pull things, you don't download, you pull them into R, and R downloads them in a specific way. So we kind of just put it there as a repository. And I think we might even be able to just send it in the chat as well, Neha. Okay, so a few other things about R. One of the main areas that I like to show people is the tools area, and mostly the global options. So the global options is really important because this is where you can change your version of R if you have multiple versions installed. Because especially if you want to use a specific package that was built on an older version, sometimes you have to revert to those versions of R in order to use the package because it hasn't been updated to run on the newest versions. So you may have to do that if you have to go find like a script that's really specific for something that you're doing in your data sets. One of the other really nice things about this area is called the appearance screen. And so this is where you can set your colors. I really like this Mare Bivore, but you can see there are all these different ways you can adjust your color settings. And what this is doing is it makes, for example, your comments a certain color, your function names a specific color, and then character character arguments, certain colors. So it makes following your script a lot easier, especially if you have to identify an error. It really helps to make sure, for example, like if I forget this thing here, it does this, and I can tell that the script is messed up because everything is turned green. Okay. Any quick questions on that? Is anybody having an issue with the script? Everyone has it in their... Okay, so we're going to start just moving through the script, and we're going to start with the most basics. And the whole idea of today is that we're going to basically learn how to think like R kind of thinks, is the best way to put it. And we're going to learn how to do what I call the old school way of coding R. So that it's the way that your professors probably learned how to code R, and you might have been taught how to code R. And then knowing how this works will help you understand how more advanced workshops that are going to happen in the future, like tidyverse and Tibble and things like that, work, because the theory behind all of those is based off these kind of you know, all the stuff that we're going to talk about today. So this will really help you start learning how to do more advanced things in R. Okay, so first things first, whenever there is a hashtag in front of a line, it is called a comment. So that means that it's there and you can read it, but it won't go into the console and be executed. So you have to execute things from your script into the console for R to actually process them. So in order to do that, you can you usually press Control Enter. You can also click, if wherever your cursor is, the blinking line is, you can click the Run button, and it will run that line of script. Like for example, this browser, if I click Run, it will open the browser again, and it will also have executed it down here in the console. I can do that again by pressing Control Enter while I have my thing over it. And you can also do specific things like highlighting areas, and they will, and then if you do Control Enter, it will run everything that's highlighted. So you can run multiple lines of script at once if you have everything working together. And then you can also copy things if you want to. You can copy subsections down into the code. Like if I just want to do 1 divided by 10, I can copy it down like that and press Enter, and it'll do it. Or I can subset and press Control Enter, and it will also execute it into the R console. So there's a lot of ways. You just got to get used to what you like. I actually like Control R, so I changed my settings. If you go into the global options, in here somewhere there is a lot of, if you find, I forget exactly where it is, but somewhere in here you can change all of your hotkeys. So if you want to change your hotkeys, you can also do that. But Control Enter is the common way to execute R functions, or R command line code. So let's get started. We're going to start with the most basic things you can do in R. So R is at its core a statistical analysis software, written in the S language is what they call it. So if we go to this first line on 26, that you can do all forms of basic arithmetic. So one thing here is if you see a hashtag with a greater than arrow, and then this kind of like bracket 1, 1, all I've done here is put what's going to come out in the console up here so you can see it if your execution isn't working. It's not in all the code, but in some of it I've put it there just for the sake of visibility. And I'm going to zoom in a little bit for you guys so you can see a little bit better. And everything in this R environment is click and drag, which is really nice. So you can make all of these areas whatever size you would like. Okay. So let's do one. If we click on line 26 and we press Control Enter, 1 + 1 = 3. So R can do very simple things like math. It also knows how to do things in the proper order of operations. This is all the same, so it won't be an issue. So 1 divided by 100 times 20 is 0.2. We can use parentheses to do addition before we do division. Simple things like this. So I'm just executing these down. We're going to work through some of these really quickly. Just if you have a question, you can ask Kevin, and if we want to come back to it and explain it in more detail, we can. So it also knows how to do simple things. Like R has built in what pi is. So R knows that pi is 3.141593. So you can do pi squared, you can do pi divided by 2. So you don't have to write in 3.14. So there's a lot of these little built-in, pre-built objects is what they're called, that you can use within R, which makes some of this stuff a lot easier to do. So that's very basic arithmetic. You can do that. So if you need to get a quick number, that's great for R if you got to do some quick math. We can also do, there's a lot of base stats in R that you can do. So you can also do exponentials, so for example, if I want the square root of 4, the square root of 4 is 4 raised to the 1/2 or raised to the 0.5, and that's 2, right? But do I really want to have to write this out every time when I'm doing stuff? Well, you don't have to, because there's functions, especially for these very easy tasks, that make your life a lot easier. So this is what these are called. They're functions, and they're usually, in my screen, they're on white, and then they're what's called the arguments are put within the parentheses. So if you do a question mark and then the name of a package or a function, it will bring it up. So if we execute question mark square root, it will bring it up over here on the right in the help menu. So the help menu is the greatest thing that you'll ever encounter, and also Stack Overflow. Nobody who writes R just sits down and writes R for the most part. You Google it, look up help. Anybody who tells you they just sit down and write a bunch of R, I mean, there is a point, but you also revert back to the community a lot and figure out, hey, how can I do this quicker? It's not working. I don't understand the error. R is notorious for giving you an error that makes absolutely no sense and doesn't explain how to fix it. So you will spend a decent amount of time Googling the internet to figure out what is this error I'm encountering and how do I resolve it. But on that same note, if we learn these basics, some of the prompts that R comes out as errors, if you understand the vocabulary, you will likely be able to potentially resolve a lot of these errors as well. Control Enter is not executing for me. Are you on Windows or are you on Mac? Okay. So if it's not working, just click on the script and hit the run button. Yeah. So if you click on the line and then you hit the run button right up here, and it should execute the lines as we go. Okay, so for examples, let's go back to so the question mark square root. We have this help menu over here. So it's going to give you a description. It's going to talk about, so in this one, it's called math fun, but it's actually the absolute value and the square root function. So it computes absolute values of x and computes principal square roots of x. And then if you come down here, the arguments, it explains what you need to put within the parentheses. And this is an example of what it should look like. Square root of input value x will give you your output. So here, again, we're asking for the square root of 4. If we run that, it's going to give us back 2. There's all kinds of these functions. There's log, there's, any base math that you can think of, there's probably a base function that you can use. So again, if we want absolute values of numbers, we can say ABS of -5, and it gives us back 5 down here. So if we get into a little bit more complex of a a function like log, I'll put the question mark here, we now have in the right here, we have two arguments. We have an x argument and a base argument. So this is the, when you get into more advanced functions, you can have hundreds of arguments. For example, if you if you go like, if you ever do like GWAS and want to run gapit has like over 100 arguments within the gapit function. So you just separate all of them by comments. So here we're saying I want to take the log of 10, but I want to use base 10. And that will give us 1. But sometimes you want to do log base 2 or other base logs. And by doing the comma base equals 2, we're doing the log base 2 of 10, which is 3.3. Okay? So these are very basic concepts of this is how R stacks everything together, and you can, and we'll see much more complicated, not complicated, but there's more arguments. And then if you don't know which arguments, the nice thing about RStudio 2 is that it helps you finish script. So I'm just going to write this in. You don't need to copy it. It's just for an example. If I'm writing log, it will bring up all of these examples of things that I could potentially use, right? Do you want to do log 10? And it's going to give you the help menu here too, right? So and it also shows you the arguments. So if I want to do log 10 again, I can do this, and it's going to actually help me finish what I'm doing. See, it knows the argument there, and it's going to tell me this is the most likely thing that you want to use. So base is the function, and 2, and I can execute the code again. So you don't necessarily, if you kind of remember how it works, you don't, in RStudio, you don't have to rely on going back to the help screens all the time. You can kind of do it as you work. Okay, so another example of this is, for example, we have pi, but do we really need to save all of the digits of pi into our memory? We can round very easily with the round function, and then we can use the argument digits equals 2 to round it to 2 digits. So we do that. 3.14 is commonly what most people use for pi if they're doing quick analysis. Okay. Are we having some issues, Kevin, or should we keep going?
I think you're okay. There's one individual that can't find the run button. So Steve, if you could point it out, I can't take a screenshot and post it in the chat for some reason.
Okay,
so
so
I'll look into it.
The run button is right here. It should be in the top right corner of your script. If you're in the R console, there is no run, but well, there is, but we're working in the RStudio, so you need to open the RStudio package. Okay. He didn't have a script open, or she didn't have a script. Okay, cool. Yeah, so you have to have a script open to see the run button. Okay, cool. Let's move forward. So the next most critical first step of R, besides understanding how functions kind of work, is assigning assignment statements and making objects. So by using this symbol less than dash or hyphen, we can assign the object A the value of 5. You can do it the other way as well, but it's not conventional. And some people, it'll drive some people crazy. You can also do this. These will all achieve the same thing, but this is the classical way to code in R, and this is how people like to read R. It's kind of changing to this, but I don't. This can cause you troubles when you get into advanced scripts and things like that. So I recommend that everyone sticks with the old school assignment statements. So if you execute A less than hyphen 5, it doesn't output anything. But if we look over in our environment, we now have an object called A, and its value is 5. So if we then run A, we tell R to do like run A, it's going to say 5 because A is 5. Yeah, so again, if I do a equals 5, it has now assigned it here again. So you can do any of these ways, it will work, but the top way is the one, this is conventional. Okay, so R can also spell check for you, which is nice. There's also a really nice function you'll use a lot, which is called print. So print basically will just it'll tell R to execute things into the console. So print A, it's 5. It's equivalent to saying A. When you get into more advanced things, you can use it you can use print to say hello, and if you're using characters, it has to be in quotes, and then it'll say hello. R has responded by saying hello. Okay, so this is if we try to execute line 72, we have an error. So the reason we have an error is because R is case sensitive. So you have to make sure that when you look at something in the helper or something like that, if you have a case missing or an S at the end or something like that, it won't work. And that could be a very simple issue, is that you've misspelled or you have a case somewhere that there shouldn't be. And we'll talk about that in a few lines, how you can keep your methods consistent to try to avoid that. Okay, so as you build more objects over and over, and they will start to stack up in the environment. But you can also remove things from the environment. You can either sweep the entire environment, or you can select. If you go to grid, you can select individual ones to sweep. And if you're going in the terminal way, that when you start going really advanced and maybe using supercomputing, you're going to use the remove functions called ls. And oh, sorry, I'm getting ahead of myself. So if you're running base R, you're running terminal R, like in CMD, ls is going to list everything that's in all of your objects that are saved in your environment currently. So if you learn on old school R, just like the terminal, you would have to, if you forgot what you had assigned, you would ls to figure out what the names were, because you don't have a script, you're just writing as you go. You can also use the function objects, and it will also list all of the objects in the R environment down here. So we'll show that again later once we have more objects assigned in the environment, and I'll show how that works. So say we want to remove, like I was just talking, we want to delete A. We don't want that object in there anymore. Well, you can either just assign A a different number. Like if you want A to be 7, R just changes A to 7. So you have to be careful of that. It will overwrite, and it doesn't give you any notice. So you have to keep that in mind when you write your scripts. But if you want to just get rid of A, rm means remove, and then you can put the object name in as A. And then A is gone. It has been deleted from here. If you type ls in the console, there's nothing there because we deleted it. Now, if you say you have hundreds of different objects in your environment, and for example, it's bogging down your memory. So R runs on your RAM. It runs on your virtual memory. So that's how you can be limited in how much you can run. So if you don't have if you only have 2 gigs of RAM in your computer, the amount of things you can save in the R environment will be less than if someone who has 32 or 64. And that's what you really need to do, like huge genomic or phenomic data sets. You need to get a lot more RAM so you can process through the data. Similar thing is seen if you go into Excel and you try to open a huge Excel sheet and it just is like slow and freezes. It's probably because you have limited RAM in your computer. So they work in a similar way. But this function rm and then list equals ls. So what it's doing is it's telling R to make a list, which we'll talk about later. And then you're saying make a list of all of the objects that are in the R environment, right? Because the ls prompts to return all of the names. And then it's just going to remove it. It's going to delete everything. So this is like a code within a code. And this is how R works, is you can stack codes and functions within each other, and you don't have to always assign objects all the time. And we'll see that a lot as we go through the script today. Okay. So removing is common. Honestly, this is only really used if you are in terminal R or in the old school R console, because in Studio you'll just hit the broom button if you want to delete, or you'll go in and you'll manually select which ones you want to take out. It's just easier that way, in my opinion. There's no need to spend time writing a bunch of script to do it, unless you need to do it, and if you're going to just run your whole script and you need to tell R to delete things as the script goes to continue the process. So think if that's something you need to do, is you need to delete things to continue your analysis to go. Those are what those functions are for. Okay, so there's another trick to R where if you do anything with an assignment. So if we just run a = 5, we don't get an output, right? We just get an assignment. But if you put everything in an all-encompassing parentheses, it tells R to do the assignment, but also to print. So it's gonna assign A to 5, and then it's going to also tell me what A is. So it's basically like doing these 2 lines here and this one in one step, if that's what you want to do. That was on line 63 and probably 65 if you didn't add these other few things in. And I'll save if anything that we add in, I'll save, and we can give a final script if really necessary. But the whole idea here is to have everybody just kind of follow along. Okay, so we're on around line 92, ish, unless you've been adding. So we're going to talk about. So we've been talking about assigning an object like A, and an object can be named anything, but it has a couple of rules. The object has to start with a letter. The name has to start with a letter, and it can only contain letters, numbers, underscores, and periods. So you cannot start object names with numbers, which can be a little frustrating, especially in phonomics data where you usually want to start with a date. So there's ways around that but there's a few common ways that people like to name things. So this is the method that most people would like people to use in the community. It's called the snake case, where everything is lowercase and then your words are separated by underscores. So if you can remember this is the way that objects should be assigned if you're going to use multiple words, is using all lowercase and all underscore, because when you add in things like capital letters for every word, it's not only more work for you to type this in every time, it's also gives more opportunity to leave a lowercase in where it shouldn't be, and then your code doesn't execute, and then you have to go back and proofread everything to find out that your C wasn't capital when it should be. The period method works well as well. I mean, it's not much different than the underscore. I just think the underscore is easier to read personally. And then as an example, I took off the internet. Some people are crazy and do whatever they feel like. I'm completely honest. When I first started writing R, I probably wrote my objectives something like this, or in some form or another like this. So you'll learn to make your life easier. And it's just, once you start writing R more and more, you're going to learn how to make your scripts faster, how to make your reading your scripts over and over again much easier. So the worst thing in R is to have to go through a 1,000-line script and have to find an error, especially if it's not in a spot that is easily identifiable. Okay, so a few more examples here. We're going to make an object. We're going to make a character object So we can make character objects by using quotes, and this is what's called a string. So every quote is a string. So this is one string, and if we had another, that's another string. But you wouldn't write code like this, but that's an example of another string. Everything in a quote is a string. And we're not going to talk about this today, but you can break strings. That's a little bit more advanced, and you have to use more codes to do that. But maybe in the next course, we'll talk about breaking strings. So we're going to assign this object R workshop as really fun. And then we're going to try to run this next code, and it doesn't work. And the reason it doesn't work is because we accidentally put an S at the end of it. So it has to be exact. It doesn't assume anything. We're working with a computer here, so it doesn't know like, oh, you meant this, so I'll figure it out. It has to be exact. And then here's an example of, again, it's not working because we have a capital R instead of a lowercase r. So those are simple things which can be easily like easy mistakes that happen, and R is all about the details. So I had a professor that I learned a lot of these introduction things, and he would always say the devil is in the details. So if something's going wrong with your script, the first steps is probably going to be a spelling error, a capitalization, a punctuation, a comma where it shouldn't be, you missed a quotation, you missed a parentheses, something like that. And we'll talk about how that can be affected in a little bit. Okay, so we're going to start moving a little bit forward. Is there any major questions on, is anyone not understanding how to assign things? Okay, so very basic. So the majority of what we're going to talk about today is data structures in R and how they work and how they can be subset. Because if you don't understand how the data structures work in R, you're never going to understand how to give the proper information to your packages that you want to use. So everything in R is essentially based off of vectors, and vectors are a single dimension data. So basically, it's only the X of a Excel sheet, just the X of the first row, just the first row, I mean, and it can be as long as you can store it in R. So the things about these is a vector has to be the same element. So what I mean by an element is there's 6 types of elements. There's logical elements, which are true false. So R can work in true false, and we'll talk about that. There's integers, which are numbers. There's also doubles, which are, again, numbers. There's character vectors, and there's complex and raw, which we won't really discuss today because you almost never run into these that you know of. You're almost always running logical, numeric, or character vectors. So we can, again, run this question mark vector, and we can get some information about what vectors are and how this function work, like what they are. But most people don't actually use the function vector in R. A lot of people use the C function. So I think it'll pull up. If you do question mark C, so this is called the combines value function. And what it does is it's kind of like concatenate, where everything that you list separated by commas will be turned into one vector of elements. So the idea here is we're going to make a vector of numeric values, -1, 0, and 1. So whatever order you put these in the parentheses is the order it's going to output. So this is going to be location 1 in the vector. This is location 2 in the vector. This is location 3 in the vector. So if we execute that, it will print out a vector. You can also assign this to a value. A lot of what we're going to do today, I'm not going to assign, just because we want to see the printouts right away. So a really important thing to remember in R is knowing what data form you're in. And by that, I mean like character, numeric, logical. That can be a very easy fix if you get an error like error, this is not a character class. So you just have to change it to a character class. So the class function is a very important thing. So again, we're stacking functions. So we have the class function, open parentheses. We then create the vector within the class parentheses, and then we close the parentheses for class. And the nice thing about RStudio is wherever you click in these parentheses, it will show also the corresponding parentheses. So once you get into like really advanced like stacked functions, this really helps you figure out if you have enough closing brackets or parentheses to complete the script. So if we run that, it's going to tell us this vector is numeric. An example, if we delete this one parenthesis, it's going to give us a plus down here. And what that's telling us is that the script line is not complete. So it's looking for something else. You can either add more things to it, but the simple solution is it needs a parentheses and completes. So if you see a plus in your script, that means usually you're not done with executing that line of code with what R needs to finish. Okay, so again, we can make character vectors, but every single line in the vector needs to be in quotations. So this can be very tedious if you have to make a very big vector. But so there we see, and then we can tell it's a character vector because when it prints, it's also in quotations. And if we do the same thing with class, it says it's now a character vector. So I'm going to show you guys something really quickly, and we'll talk about it in more detail. There's a lot of these things called as functions. So you can do like as dot numeric, or let's do character actually. And then you can put in your numeric vector, right? We put in the numeric vector here. So what this is going to do is it's going to convert it. So it converts it to character. So these are simple functions that can save you a lot of time. If like you need a numeric, if you need a bunch of characters, but they're all just numbers, you can write them in as numeric and just switch them instead of having to write the parentheses hundreds of times. So those are very important functions that you'll use all the time. Okay, so the next major area is called logical vectors. So logical vectors are probably the most important type of vector in R because this is how you subset everything. Once you learn how to subset with logical vectors, you'll be able to hack and slash your data frames and your matrices very, very easily. And the upcoming workshop where they talk about tidyverse and plier and dplier and tibble and all those things is essentially completely based off of logical vectors and subsetting with logical vectors. So you can these are what are called special characters. So anything in yellow is a special character. And on my screen, it might be different on your screen. But if you write true in, R knows it's true. It just repeats true back. R knows false. So you can make vectors of just true and falses, like this. And we'll explain how that really helps in a little bit once we get into logical operators. You also can save yourself a lot of time by just doing T and F. It's the same thing. So if I make CTFT, it returns the same thing, true, false, true. So R does interpret certain things. And if we run the class again, it's a logical vector. So the class function is really good if you're trying to put something in and it's not working. You're like, whoa, why isn't this working? And it's like error, not character, error, not numeric. just convert it to what it needs to be, you know, like that's the easiest way to do it. One important thing about logical vectors is logical vectors are essentially binary. It's ones and twos. True is 1, false is 0. I mean, not ones, it's ones and zeros, sorry. So if I convert this to a numeric vector, it's going to come back as 1, 0, 1. See? So this is really, really important too, because you can essentially write scripts that return ones and zeros and convert them to true falses, or you can write scripts that keep things as true falses and convert them to ones and zeros to subset. So it becomes really useful once you learn how to subset with vectors. And there's been people who have really taken this to the next level, and there's great functions and packages that do it internally for you that will be discussed in the future too. And this was out of place, but we talked about this already, the combined values vector. Okay, so we're gonna kind of cruise through this. There is a lot of script, so most of this should kind of just flow together. And we'll stop if there's a major question, but Kevin should be able to help with this. So we kind of talked about this already. Sorry, sometimes when you write a lot of script, you repeat yourself sometimes. Okay, so this is a question. This is kind of important. It's a quirk of R. So R does numeric vectors in two forms. It does them in integers and doubles. And R always does things in default in doubles for numbers. And it's not entirely important to understand the difference between these, but it can be important when you're doing arithmetic. So if we ask for the class of this, it's just going to tell us numeric, but we really want to know if it's a double or if it's an integer sometimes. So the reason we want to know this is because doubles are what are called floating numbers. So R will somewhat round things, and if it's in double form, you can't do certain arithmetic because it will give you out a value that you weren't expecting. So for example, if we set x to this crazy number and we use type of, it will tell us that x is a double. If we call x, then where did all our decimal places go? They're hidden in there, but so if you did a division of x by this number, because you're assuming that it's this number now. Okay, that worked. Okay, we're gonna keep going. That shouldn't have worked, but it worked. This is the example where it'll show. So we're gonna assign x to the square root of 2 raised to 2. And if we do that, it should be 2, right? That makes sense. Square root of 2 raised to 2 is back to 2. But if you subtract 2 from what we think is 2, because it's a double, we get this number. It's because it's a floating number in R from the double. It should be 0, right? Because that you would think that is, but there's just these there's very, very small number that R can put onto things that makes this happen. And this, I just want you to remember this because we'll run into it later. And it's an easy way to figure out why you're getting, you know, these special characters when you're like, this doesn't make any sense. It should be 0. So I'm gonna make a vector now, and I'm gonna show you why this is happening. So the doubles format has 3 special characters. It has NA, it has infinite, and it has negative infinite. So this is vector double, is what I'm calling that, and we're just gonna make it -1, 0, and 1. And that comes out just like that. We can then ask what it is. It's a double, because they always do doubles first. But if we divide the vector by 0, we get negative infinite, NA, and infinite. Now, everyone that took math learns that anything divided by 0 is 0. Are we all in agreement with that? Or it should be in lamest terms. So you would kind of assume that this would all be 0. And this is a quirk of R with division specifically, of 0. Multiplication is fine. It will come back as all zeros, right? So if you get negative infinites and infinites in your numbers, it's because you're working with zeros. I mean, you might be dividing by some extremely small number that R is using the doubling. And it's just a quirk that you have to learn with. I personally do not like having all of these 3 special characters in my work. I like NAs, so I try to stay on integers as much as possible. So we can check this vector for special characters. So these are called the check functions. We're going to do the same thing we did up here that made the infinite NNA and infinite. And we're going to ask, is any of these NA? So it's going to say no, yes, the second value was NA, and the third value is not an NA because it is negative infinity, NA, and infinity. We can then ask if it's NaN, which is essentially the same thing, but if it's an integer, NaN doesn't exist. But here it'll come back the same thing as NA, true. We can also ask, is the division outputs finite? It's going to say no, because they're all special characters. We can also ask if they're infinite values, which is true. So you can use these things to identify weird anomalies in your vectors when you do basic arithmetic, to identify if you need to go back and maybe switch to integer. So let's talk about how integers are made. Integers are the same thing, and if you want to force R to make integers, you have to put L's after the letters. I mean, after the numbers, which is really annoying. But you could just, once you put it in as a double, you can use as.integer and make it an integer as well. So always remember those as dot numbers, functions, and you can switch things much easier than having to write L. Like, not a lot of people want to do that. Yeah, so, okay. Yeah, what's the difference between NA and NaN? There's no difference when it comes to doubles. NA and NaN, it's the same thing, but doubles will return NaN. And if you're an integer form, NaN doesn't exist and only NA will be returned. Also, infinite does not exist in in integers. It only exists in doubles. So it's just an understanding of like how the different data types work. Okay, so we've made the integer vector now, v integer, and we can ask it, and now we have an integer. So this is what I was talking about before. Remember, this is the doubles vector, but we can use the as integer function and convert it very easily, so we don't have to write the L's in. And again, this is going to show us that by using the as integer, we've switched it to integer. I'm going to just print int really quick to show you. It looks exactly like the doubles one. They look the same when they print out. Now, if we do this division, whoa, what happened? We're dividing the integers by 0. Shouldn't it be 0 or NA or 0, 0, 0? Well, we're going to just use this as an experiment to work through using what you know to figure out what's going on. So first question, if we do is.integer, we're asking, is the division and returning an integer vector? And it's saying no. Okay, so something is happening to take this back out of integers, even though we started with an integer vector. So let's ask it what it is. It's a double. How did it become a double again? Okay, maybe it's because we're dividing by a double. So let's divide by an integer. And we ask that, and it's still a double. So this is where, understanding how R works is very important, because if we do this one here divided by 1L, we still get a double. And when we multiply by a 0, we still get a double. And when we multiply by 0L, we get an integer. So why is this occurring? This is because R always takes the more complex of the two and turns it into that. It converts it. So if you have an integer and you divide by a double, you're always going to get a double. Or if you multiply by a double, you're always going to get a double output. If you divide, it seems that even if you divide by an integer in R, you're still going to get a double. I don't know why that is specifically. I'd have to dive into it more, but the idea is not to fixate on doubles and integers. It's to show an example of if something comes back and says your data is a double and it needs to be an integer, you have to figure out how to make things the correct format to make your functions work. And these simple tasks of figuring this out and working through the problem is what you have to kind of train your mindset to do in R to make some of these things work. Okay. Why is it double? Because doubles use less memory. I'm pretty sure that's the reason why R uses doubles. Yeah, you'd have to go into the scripts and ask the creators of R why that is. I wouldn't fixate it on it that much because for the most part, if someone codes their stuff to make it a double over an integer, they're making their coding way too complex. They should work interchangeably the most times. Okay. So here's an example of that most complex always wins. So if we make, we try to make a vector of a logic and an integer. Integers are more complex than logical statements. So it's always going to turn this into a integer, right? So it's going to convert true to 1. If we try to do a integer and a double together, it's going to convert everything to a double. And if we try to do a numeric and a character, which you shouldn't do because you should always remember vectors should always be the same data type, it's going to change them all to character because character is more complex. So it's going to put parentheses around your 1.5, like here. So you can cheat the system and it's going to work, but you don't want to confuse your script a lot if you don't have to. Always stay consistent in your writing is the best thing I can tell you, because if I saw this and I didn't know it was an example, I'd be like, what is this person doing? You can't have a numeric and a character together in a vector. They have to be either all numeric or all character. In theory, but R has made it, with what I call, easy logic, that it will just fix it so you don't run into some of those errors. Okay, so this is just examples of understanding data structure in R. Again, don't fixate on, you really just need to know the difference between numeric, logic, and character. The other thing was just really an example to show you, you can run into these issues. Understanding and working through it is really important to figuring out your errors, and not because you can spend days and days and days fixing errors in R if they're complex. Okay, and then we can show here you can also convert what is going to be a double back into an integer, and it's going to give you out all NAs. And that's just because, like we said, integers don't know what infinite is. They don't know what NA is. So it all is going to get changed to NA because that's the only special character that integer uses. And it makes cleaning your data later, if you need to search for just NA, it's always easier than having to search for infinite, NA, NaN. It's 3 extra steps. The warnings, so this is an example of a warning. So warnings are different from errors. Warnings, the code will still execute and you're getting your output. Errors, it will cancel the execution and you'll have to figure out what's causing that before it will execute. So this is just telling you, be aware that this happened moving forward. And you'll actually see this a lot in a lot of packages where there'll just be warnings, like pages of warnings on your output script, and the creator's like, don't worry, everything's working fine. So just be aware of that. Okay, so we're gonna get into some things that are really important for simulating some data. Is there any questions on data types before we start? I think we're good. I think we answered everything about doubles and integers. Hopefully I didn't confuse anybody too much with that. Again, do not overthink it. Just be aware of it. Okay, so we're gonna start talking about making repeated numbers. This is some of these easy things that will save you a bunch of time instead of having to type, for example, 21s in the C. So the rep function is just repeat or replicate an element. So we're going to create an element called x, and we're going to repeat the number 1 20 times. So if we do that, we call x, we now have a vector of 1 20 times. That is a lot less work than having to do C 1 1 1 1 1, right? Like nobody wants to do that, and it looks ugly. So there's simple things like that. If we want to make sure that it did it correctly, we can use functions like length, and that will tell us the length of x is 20, which is right because we told it we want 21s. So those are simple things. We can also repeat vectors. So we can repeat a vector over and over again. So if we want it to be 1 through 5, 1 through 5, 1 through 5, or 1 through 4 5 times, you can put that in as the repeat element of the vector, and then tell it you want to repeat 1 through 4 5 times. And that will create 1 2 3 4 1 2 3 4 1 2 3 4. And you can further simplify that by saying, I want to create a, you can do 1 colon to a number. And what the colon does is it says you're assuming that the vector goes from 1 to 4 and it includes 2 and 3, right? It's saying you want the whole range from 1 to 4. But that still has to be within the C vector function. And this will do exactly what we did above, but it saves you some scripting, and it looks nicer and cleaner. You can also use the rep length function, and it does essentially the same thing. Here, it does exactly what rep does, but if you prefer this, it does the same thing. Except you give it the length, right? If you don't want to repeat this 5 times and you actually just want, which would be 20, and you just want 18, what R is going to do is it's going to do what's called recycling. So it's going to recycle the 1 through 4, but it's going to stop at location 18. So you're not going to have 3 4 anymore. So this is very important, and we're going to talk about this consistently through these data structures, how recycling works. And this is one of the main things to be aware of, and we're going to talk about that in more detail in a few minutes. But wherever you tell it to stop, it's going to stop, and it's either going to recycle continuously like this, recycling, 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 and it's also recycling here, but it's not completing the recycle, so it's stopping early. It's a premature stopping of the vector. Okay. So let's talk about making a sequence of numbers. So instead of, so for example, what if we want to skip we only want to do odd numbers, right? We want to skip 2, 4, 6. We can write it out like this to 15, or we can use the sequence function, which we see over here, and you can read up on if you want to. So essentially what you do is you tell it what number do you want to start at, what number do you want to finish, and at what value do you want to skip through. So it's going to go from 1 to 15 by 2s. And if we execute that, we get exactly what we did here. So yeah, it's not a big deal when you're maybe doing 7 values or however long this is. But imagine if you need to do that into the thousands or the millions. You need to be able to go to here and switch this to 10,000, right? And run it, and it's going to make all of those numbers for you. And you can make this by can be very complex. It can be some crazy mathematical value that skips to specific numbers. So just keep that in mind, that these don't have to be simplistic like 2. It could be like the natural log of 10 divided by, you know, whatever you need. And then you can further simplify functions, specifically these very base functions. You don't have to write from, to, and by. If you look at the order in the help menu, they're specifically placed in this order within the script, because R will assume for certain functions that you mean from, to, and by. So once you learn the scripts, you don't have to write them in. And you can do that. We'll see that when we talk about matrices and other things, that you don't have to technically write from equals, to equals, by equals. It's nice when you're learning, but once you memorize these commonly used scripts, you can just do that, and saves you a bunch of time too, because you're not writing from, to, or by. Yes, yeah, it's normal, Sarah. It will only usually go up to a certain point, and then it will stop. If you want to see the full thing, you have to pull it up into a different. I can show an example of that really quickly. So if you want to see the full thing, for example, 10,000. This should work, but we'll check. So if you use the view function, capital V, and you put that all within it, it should pull up a screen that you can then scroll all the way to, I guess it only went to 5,000, but you can go to a certain extent. But if you, and we'll get into this in a second, but if you assign it to X, for example, you can always go into X and ask for like number 8,000, and it's going to bring back, maybe sequence only goes up to 5,000. I've never noticed that, but that might be an important thing to notice for this, that it only goes to a certain limit. Yeah, sequence might be limited to 5,000 inputs, so it seems like it is. So there you go. There's a trick that I didn't know, because I don't think I've ever used sequence to that large of a data set. So simple things like that, you just learn, right? You have to figure them out as you go. So that's a good example of running into an issue and trying to figure it out. And that might be in the literature somewhere in here if you read through it. And I'm sure there's ways to get around that. Okay, so those are making simple, just random, like full sequences, and then just repeating the same numbers over and over. If we want to make random numbers, which is really important for example, experimental designs and randomizing your experiments, you can do that in R. It's really easy. RUnif so that stands for random uniform. If we do that, there's all kinds of random uniforms. There's the P, the Q, R, and D. It stands for density, probability, quantile, and random. So I usually just use the random one. So R, it's asking how many samples do you want? How many numbers do you want? 20. We want the minimum to be -1 and the max to be 1. So it's going to pick numbers between that range. So if we execute that function, we then have 20 random numbers. And you guys are going to have different numbers than me because they're random. And we're going to talk about in a minute how we can make it so that we all see the exact same numbers, even if we are generating a random set. So if we summarize that, this function is really nice summary. It will give us some of the basic statistics of what we just had there. If the mean is 0.13, we have the quantiles, the median, and the max and the min. And if you read some of these things, a thing about RAND-UNIF is you'll never actually be given negative in the extremes. So if you need the extremes included, you need to go farther beyond them. So you'll learn things like that. Okay, so if we want to all see the same data, there's this function called set seed, and a seed is a value that allows randomization to be, it's random, but everyone will get the same random data. So we can show everybody the exact same results. So the thing with set seed is that this number can be whatever you want in here. It doesn't matter. But for us to see all the same thing, we all have to be at 1 or the same number. And we're going to generate the exact same data. But now, if we run rand, we should all have the same numbers. Negative 0.468, 0.55 at the end. An important thing about this is that if I want to run rand again, you always have to do set seed, then the number generation. As soon as this is concluded, the set seed is gone. R ignores it. You have to do it again. So you can't just run rand again because we'll get different numbers. You always have to run set seed rand. And once it's defined, rand will stay the same until you define rand again. If we do the summary, we should all see the median at 0.2, max 0.98, things like that. So if you're teaching, in this instance, this is really great. If you're simulating data and you want random numbers every iteration, this would not be a good idea because it's going to give you the same results every time, unless you change the seed every iteration. I wouldn't use this unless you're doing exactly what we're doing now, where we're trying to teach. Okay. And yeah, this is what I was saying again. If we run this one again without the set seed, we will have a bunch of different numbers again. So here's just an example, a little statistical example. Everyone that if you're still taking stats or you're learning stats now, you'll start to learn this about random sampling. So if we're random sampling, we're going to assume that the plot has just an even distribution of data all over the place. When we pull small amounts of data, like 10 samples, and we run this function hist, this is going to make a histogram. And you're going to see it looks pretty good. So this one worked very well. If you run it a couple times, sometimes it will change. You'll get stacks, but it's working really well. If you run it with, I'm going to change this and show you plot. So this is just going to show you that that's what it looks like. And I know that this is okay because we also looked at the histogram. But when you get into really large samples and you run, like, this is 1e to the 6 is a million. So you can use e values in R as well. We can get out all of these numbers. And you would want to assign them to something if you're going to use them. I'm going to switch this to plot too. I forgot to switch this. I think the plot function is nicer for this. And we plot 1e to the 6. Oh, you have to get rid of the breaks. Okay, so this is an example, something that R can do sometimes is it gets bogged down. So see how we have not got the return. If this greater than sign doesn't return and you execute another code, it means R is still thinking. And this was not an issue yesterday, so we might have to crash R. So sometimes if it freezes, you can wait it out. Okay, yeah, that'd be great, Neha. We'll take a break as soon as we get through these random number generations. Unless I have to restart R, then we might have to do it right now. Okay, so if you run into this issue, sometimes the best option is to just turn R off and turn it back on. You can try going into session and interrupting R. Or trying to terminate R. So I'm going to terminate R and see what happens, and see if it'll come back for me. And this is something that you'll run into with R a lot, is that it will get bogged down, and sometimes you have to restart it. So I'm gonna. Is anyone else having this issue, or did I just get a glitch in my? Okay. I'm just gonna restart R really quick. Okay, so if you're having that issue, you might have to. Yep, turn it off and turn it back on. Exactly. Crash it. Okay, where were we? Okay. I'm gonna reduce this number just because it might be the size. It shouldn't be the size. It shouldn't have any issue running a million numbers, but let's run 1,000. And you can see that looks like random data, much more than this does, right? So the more that you sample, the more randomness you actually get. That's just the simple statistical theory that you'll learn, and you should be learning in your classes as well. Okay, so we can also generate random numbers from normal distribution, which is really useful, especially if you're simulating data, because you want to use normally distributed data to run statistical theory. The R norm function does that. Yeah, see, you can get these warnings like I saw in the chat. Again, it's telling me that it's because I put the breaks in there, and it's like, whoa, this is not you told me to make a plot, not a histogram. I don't know. I'm just going to ignore it. So it's fine. Don't worry about that here. It's good that you noticed it though. Okay, so the normal distribution functions here, again, there's P's, Q, R, and D, just like the other one. They also have binomial ones. So if you want to do zeros and ones, you can do that with like R binom, I think. And that's really good if you want to simulate zeros and ones at specific probabilities. And all of these things are available in the base stats. So what we're doing here is we're gonna simulate 10 numbers of a distribution of 0 with a standard deviation. Sorry, a mean of 0 and a standard deviation of 1. So if we run this, right, we have what you see here of those numbers, and they're going to be different because we're not using the seed. We can plot those, and they look. This is where I switched it when I wasn't planning on it. Sorry, I had those separate. Okay, so if you do the break here, set it to whatever you guys want to do. 100 just makes it really fine. So I changed plot to histogram, and then I put a comma, breaks equal 100. And this is going to make it into a histogram. So you can see that this doesn't really look like normally distributed data. This looks like our norm, right? I mean, our uniform. So if I'm going to copy and paste this down here to just show you guys with 100. And we're going to change this number here, the sample size, to 100. And we're going to histogram that. We're getting closer. So you can see the normal distribution developing, right? Because we're getting high enough sample numbers that we can see a normal distribution. And if we go even higher, we can really get a really good, like 1,000, we can get a really good representation of a normal distribution. So this is another example of, like, if you're doing simulations, especially in R, if your computer can handle it, statistically, the higher the N, the more normally distributed your data is going to be, and it's going to be better simulation of the range of a normal distribution. Okay, let's get through this last part. Maybe we should be able to get through this. We'll take a few minute break. Any questions on? Yeah, so in this one you should be good because we're generating histograms. When we were plotting up here, plot. So plot doesn't need the breaks. So if you remove the breaks, it will run this. But if you plot with the breaks command, it's just telling you, see, here's the warnings because I've included an argument. And it's like you told me to make a plot, not a histogram. So that's why that warning is occurring. We're down here, we're making histograms, so we don't get the warnings that we have a break for no reason. Okay, so we're gonna discuss recycling one more time, like we did a minute ago, because it's gonna be important for the next few sections. So we're gonna set the seed so we all get the same we're going to use this function called sample, and it's going to take 10 random numbers. And we're going to set those to X. So we should all have this set 947. So sample is another thing, and we'll talk about it more when we get farther in. Sampling is a really nice function to use. Okay, if we can then do what's called recycling. So for arithmetic, if we want to add 100 to X, it's going to recycle that 100 every time through the script until the vector has all been done. So you can do simple things like add 100 to every value in that vector. So we have 109, 104, things like that. We can also do like a skip add, right? So this is saying for X, I want to add 100 and 1,000. So it's going to add 100 to this one, then 1,000, then 100, then 1,000 to that script, right? So it's going to recycle in order. Okay. We can also do something like, and these are just examples to learn how it recycles and see the output. So we're going to make a vector of 10 ones, right? That's the example of it, rep 1 10 times. And we're going to add the series of 1 through 10. So I'm going to show you what that looks like here. So when we add it together, it's going to do 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4. And our output, if we run this all together, is then 2, 3, 4, 5. So it's added that together. And that's how R thinks things through. We can do it again here where we have, again, 1 through 10 and 1 through 3, right? These two vectors. And if we add those together, it's going to give us a warning, but what it's still going to execute. It's just telling you that the dimensions don't line up. But what it's doing is it's doing 1 plus 3, 2 plus 2, 3 plus 3, 1 plus 4, 2 plus 5, 3 plus 7. So you can do these things together to string math together if you need to make specific sequences as well. And then one last thing here on numeric vectors, and we'll take a break. You can also add labels to your vectors by doing, so we have the vector C function, and if we do x equals 1, y equals 2, z equals 4, if we execute that, we can now still see that we have the vector of values, but they also have names above them now. And we'll talk about that in more detail when we get farther along, but then you can also call out these names It's going to say those are the names of the vector values. This could be really important if you're doing genetic data, for example, and you need like the SNP number, the SNP names or something above the vector. You can also do it like this if you have a vector of just 1 through 3 and you call it, it's just 1, 2, 3. You can say names of X and then assign, and then you can say assign the vector, the character vector. And then you now have exactly what we did above here, but just in a different way. So for example, if you already have the vector and you just need to add names to it, this is the way you can do that. So when it comes to vectors, there's the logical vector like we talked about, which are true and falses. And it becomes really important to use these when you're asking what we call logical questions. And we use the logical operators for this. And common things that you've seen, like less than or equal to, equals, is important to understand that when you're asking a logical question in R, if you want to say something is equal to something, you actually have to use double equal. And you can also ask something is not equal by using exclamation mark equals. And you can also use like not functions. So you can reverse things such as is NA by putting exclamation mark is.NA, and it will say false, even though, and if you say is NA, it's going to say true. So you can use these things to ask questions like, is this an NA? It's like, yeah, it is, but is this not NA? And it's no, it is. That tells you it is an NA. So you get the same answer, but using the not can be very useful in some cases. We also have ORs, which is the straight line, which is usually right above the enter on the keyboard. So you have the backslash, and if you press shift and the backslash, you get the OR sign. And you also have and, which is a common one. So let's talk about logic here. So this is a little different than what you've been seeing before. This is because logic exists in multiple packages. So by writing the package name and then colon the function and the question mark, we can pull up exactly what we want. And this will bring up the logic, what you see here. And the reason that we did this is because if you just type in logic and you do this, you'll get sometimes what this is, and you have to figure out which one you want. That's why we use the base colon, because the one we want is in the base package here. So you can do that to pull up functions that might exist in multiple packages. Okay, so we're gonna just make some sample numbers to play with here. We're gonna make a random uniform 100 numbers from 0 to 100 range. And we're just gonna save those as random underscore numbers. And we can see here, there we have a bunch of numbers that we can work with. Everyone's are gonna be different, but it's not important for now, just the idea is what's important. So we're gonna ask R, tell us which numbers are greater than 50. So you say sample numbers greater than 50. And you run that, and it's going to tell you the location in the vector where this is false and true. And we're going to explain how you use this to pull numbers from this later. But the idea is understanding how this is translated to this, and then reusing the true false to then pull out the important data you want. But for now, we're just going to use it to understand how these operators work. So if, for example, we go to the first number up here, 20.5 is less than 50, so it's false. And that's how it works. It iteratively works through the vector and asks the question and returns the logical result. So we can add things together by using the AND function. So it's going to ask the question, is the number greater than 50 and less than or equal to 75? And then we will get the same thing. So let's check 3, which says it's true. So it's 68. So it's between 50 and 75. And it's true. We can also ask, we want numbers that are either less than 50 or greater than 75. So what this is going to do is it's going to give us all the numbers that are outside of that range, not within it. So you'll see numbers that are either less than 50 or greater than 75, which is the majority of the numbers. 13, for example, is false. If we go back up to the vector, 14, this is 13, 65.16. So it's in that area where it would be false. And this is a great time to talk about how we're tracing this. So the locations are based on, this is the first location, 1, and this is the 8th location here. And it's just an addition, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this is how we're going to subset in a few minutes when we talk about that. And this is, and understanding that is going to be really important. Velma, you have to check your audio settings to ensure that you have the right things set within your PC settings for your output, I think. Okay, so we can make this, we can stack these things. So we can do, so it's going to say evaluate this because it's in parentheses. So sample is greater than or equal to 0 and less than or equal to 25. That's saying, I want you to tell me it's true that all the numbers are between 0 and 25, or that they are between 75 and 100. So you can add compound logic statements together to get to the result that you want. So this should be pretty similar to what we did above, just a little bit different because we're going to 25 instead of 50. But that just shows you how you, especially if you have negative numbers or numbers bigger than 100, you could use something like this to subset out. And we see the true, what is considered true and what is considered false. Okay, so we can also do things like equals, and this is gonna kind of go back to the idea of doubles, and why doubles can mess you up sometimes and how you have to know how to work around it. So we can ask for the minimum of the sequence of numbers, which is 1.339. And I'm gonna use this number here because it changed from when I wrote the script. But if I put that here and I ask, so it should be able to find the minimum within the script. I mean, within the sample functions, because it should equal this. The problem is it's not able to do that. And this is one of the, I think this has to do with the doubles in R. But if you tell it that you want to find the output of the min function, instead of finding the min and then asking to look for the min with the number output, it will find it. So here it is, true. This is the minimum value of the vector that you can then pull out if you need to. So things like this are important to understand when you're using logical vectors, that sometimes you can't just type a number in. There are some other tricks and more advanced packages that will actually look for the number closest to this number. But for all intents and purposes, if you want to find the exact number, which you should be able to do, you have to use the min, the max, other functions like floor, and we'll talk about those in a minute. So just remember that. And you can also use this if you're using character vectors. Yeah, if you just do min here, min on line 413. And there's a bunch of those. If you do question mark min, There's min, max, p max, there's floor, ceiling, all kinds of things. And we'll kind of touch on those occasionally as we go through. Okay, so that's the basics of logical vectors, and we're going to use those now on throughout the talks. But we're going to move on to subsetting because this is like a huge part of pulling your data set apart and pulling out information. So if we have our sample numbers, right, we have 100 of them. What if I just want this first value? So to do that, Kevin, could you potentially help her with the audio issue? You use the brackets, so the square brackets and then the position. So as you can see here, we have the square brackets, and then those indicate the position. So by doing the vector's name plus the square bracket 1, we're going to return the first position value. If we want the 50th position, we just would change it to 50, and we get 40. And if we go back up here, 50 is 40.68. So this is how we pull things from the vectors. Now we can do the same thing we learned above. We can use vectors of positions to pull vector data out. So we can say I want the first 1 through 10 of the sample numbers, and then we pull out the first 10. We can also combine this and add, the first 10 and the last 10. So we have 1 through 10, comma, 91 through 100, and we pull those out, and it will so you're essentially making a new vector. So you see here that we're not changing to the position now becomes position 11 instead of position 91. And if we were to, for example, make this like a sample vector and assign it, we now have a new vector that is those numbers. So you can pull things and make them into new objects that you can then do analysis on. We can also we can do the recycling again, right? So we can make a vector of position 1 and 50, right? So I'm saying vector of 1 and 50. Then I want to repeat that 4 times. So if we look at that, it's 150, 150, 150. And if we then subset out that, it's going to repeat those positions over and over. So it's going to be 20, 40, 20, 40, 20, so you can do things like that as well. You can subset and repeat. You don't have to just pull data. You can pull and build. And that's how R does that. So I'm going to just show this here just for fun purposes. This is the sample function that we were talking about earlier. So in the sample function, you can, and this is a little out of place, but it's just a little break to revert back to what we were talking about. So we want to sample from this vector of heads or tails. We want to take 10 samples with replacement, and we want to have a probability of 0.5 for each one. And it's like a coin flip simulation, right? So if we run this, we then get out the response: heads, tails, 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 heads, tails, tails, heads. So it's a 40% heads, 60% tails. So we just did a very simple simulation that was one of the first probabilities things that you do in stats class. And we can do fun things like that in R by using vectors to do these simulations. Okay, so that was a little off topic from subset. I think it just got pushed down. It was supposed to be up a little higher. Let's get back to subsetting. So this is where we can use our logical vectors, these true-false vectors, to subset out from the main vector. So whatever comes back as true, for example, in here, 50, greater than 50, remember we did this, when you put that within the brackets, R is going to subset at the locations where it's true. So everything that comes out of this sample numbers, brackets, sample numbers greater than 50 will be the numbers that are greater than 50. And we can see here everything in this new group is greater than 50. So this is another important thing. If you want to know the locations in here where it's true, you can use the which function, and it's going to return this. So those are the locations in here that are true. And this is essentially the vector that you're subsetting out, right? So you're subsetting location 3, 5, 7, 8, 10, 11, 13. So you could put this vector into the brackets rather than using sample greater than 50, but if you can just use the logical vector instead, it saves you a lot of time. Okay. So let's add these layers back onto this. So we're doing exactly what we did before up here in this, and just learning the logical vectors. But we're just going to put them in the brackets to actually pull the numbers out instead of giving us back the true false. So by doing this or vector, like sample numbers less than 50 or greater than 75 in brackets, it's going to now return the values at those locations rather than just the true false. And then we get these numbers here. And then again, you can save those back if you want to save them. And once again, you can remember that complicated logical vector with the parentheses and the ors and the ands. As long as it's all within the brackets and logically, put together with the samples and parentheses, the or, and the parentheses for the next part in the order of operations, these will execute correctly and pull out exactly what you want. Now, when you get into these complicated logical combinations, you have to be careful that you don't make a mistake somewhere. So if you're not seeing come out what you're expecting, you should go back and check your logical statements to make sure you didn't make an error somewhere, or miss a parentheses somewhere. So this would be the output of the numbers that are between 0 and 25 and between 75 and 100. Okay. So we're going to do an example here with character vectors because we haven't really touched on them yet. But these techniques work exactly the same with numeric or logical as well. So we're going to do an example, and we're going to actually create a vector using the sample argument. And this is going to be kind of an example of what are called genetic base calls for marker data in breeding. So we're going to set the seed so we all have the same data. Then we're going to sample these four options of G calls, A calls, heterozygous calls are missing. We're going to take 50, and we gave them some probabilities of what would be an F2 generation of 0.5, 0.25, 0.5, and then 10% error are missing. So this is an example of how you can easily simulate data. Oops, sorry. And if we execute this, I'll print it so we can see it. We now have essentially marker calls. So we can simulate marker calls that easily. We can use something called the paste function. I think it's going to be on YouTube. The remainder should be on YouTube. It's fairly soon. So we can use what's called the paste function, and it's kind of like a concatenate function for character vectors, and we can create names to attach to the vector. Remember, we talked about putting names on the vectors earlier. So we're going to say paste G to 1 through 50 and separate by an underscore. And I'll show you what this looks like. That it looks like that. And we're going to make that the names of the vector. So what this does is now we know that genotype 1 has this call, genotype 2 has this call. Yeah, so we can trace things. We can also use what's called the table function to summarize the data quickly. So this will tell us we have 10 individuals are A, 25 are G, AG, and 9 are GG, and we have 6 missing data points. We can then use, we can ask the question, who has missing data, by saying brackets is NA character vector. And by doing that, since we added the labels, we know that individual 14, 22, 25, 36, 40, and 48 are the missing values, if that information is useful for us. And if we don't want the NA values, if we put the names function outside of that in the parentheses, it will just return a character vector of those individuals' names. We can also pull out only the first person. So you can do a call right like this that we did up here. But then you can say of those individuals by adding a bracket onto the outside of that bracket, you can say I want the individual one of that pulled vector. So you can stack these things instead of having to assign several lines of code. So you did a double subset on top of each other. So R works from left to right. So it did this first, and then it looked at this. Essentially what it did is you would think of it in this way, right? It does what's in the parentheses first, and then it pulls one from what it already did. Okay, you can also, when you have names, you can do things like, so we have this vector of names, right? And we want to find G14, we can say of the names, which one equals G14, and pull G14's data, because it's in the brackets. So then we get G14 out, and it's NA. We could change this to 37, and 37 is AG. So you can do things like that if it wasn't in order. You could also have just done 37. In this case, it's in direct order, but if it wasn't, this is a nice way to do that. You can also make it overly complicated and say something like this, which you're saying, which of the values are NA in the vector? Give me the number, and then give me the first one so I can pull out the first value so it's this in a different way that's more complicated, and you get the same answer. So the point here is to show you that there's multiple ways to do this, and there's no right way. It just depends on which way you like to think it through, and which way works best for your thought process. I usually do it this way, or if I need to be more specific, this way. But this is just showing you that there are 1,000 ways to do the same thing in R, and almost nobody does things exactly the same. Okay, so let's go back to the data set. So we've been exploring it and learning how to subset it. We're gonna fix some things. So by staying on the left side of the assignment variable, I'm saying let's pull the vector values that are A, and we actually want them to be double A. So we can assign these values here that we've subset to double A by putting it on the assignment side. And then if we look at this now, we have double A's instead of single A's. We can do the same thing to eliminate the / We just want to do AG. And we can also use what we've been using is the is NA, and assign it to a double hyphen, which means gap or blank in genetic coding. So if we now look at this, I'm on line 516, we've cleaned the data to the way we want it. And this is what's called double hat map format. And this is what you would usually use if you're doing genetic analysis. So this is just a simple example showing how you could use these subsettings to work through your script, your data set, and clean it up if it's not in the form you want. And then we can look at the final form. Now we have no NAs. We have 6 gaps, 10, 25, and 9. So it's essentially the same thing, just put into a different format using subsetting and assignment. Okay. Any questions on simple assignment and subsetting? Sounds good. Okay, so we're gonna do another exercise to go off this a little bit more. So we're gonna sample some numbers and we're gonna round them to, we're gonna take our sample numbers, which we made in the past, right, that are long digits, and we're gonna round them to whole numbers. And we're just gonna assign that to round sample numbers. Now, you can also use what's called the ceiling or floor. And instead of using the 0.5 cutoff to round up or down, ceiling will always round up and floor will always round down, no matter if it's 0.9, 0.7, things like that. So if we did this code, everything's going to round up. And if we do floor, everything's going to round down. So you can see that 21, 17. So they're in since everything's decimal, it's going to round one way or the other. We're just going to stay with conventional rounding for this. So this is an example of finding the even numbers in the vector. So there is this function called modulus, and modulus basically it's just percent, but it's division. So it's saying divide the round numbers by 2, but tell me if there is a remainder, right? So in division, we can have remainders if it's not an even division. So if something isn't evenly divided by 2, it's an odd number. So if we say it has no remainders when it's divided by 2, we can call it an even number. So if we do this and it's within the brackets, we can do things like this where we find all the even numbers, right? So everything that came out here is an even number by simply running this small script. We can also find the odd numbers by using that not function. So we can essentially copy and paste, change this to odds, and say not equal to 0, or you could say equal to 1, and you'll get the odd numbers, which are here. So all of the odd numbers. So those are some very, hopefully, good exercises to understand these subsettings, using logical operators, and using the brackets to pull things out. So this is how you can find, if you write your logical statements correctly, you can pull things out of your data sets very easily. Okay. How are we doing? Is anybody lost? Okay, I think we're good. Okay, so we're going to talk a little bit. We're going to move on now. So now that we've made it through vectors, we're going to move on to higher dimensional data. So if you ever work in multivariate data sets, which multiple variable data sets, if you're doing things like principal component analysis, linear discriminant analysis, anything like that, you usually have to work in a matrix. Also, like hyperspectral data is in usually what's called an array, and we'll touch on arrays, but there's just basically layers of matrices. So understanding what a matrix is pretty critical to a lot of data analysis. So a matrix is just a rectangular 2-dimensional data set, and each cell is a row and a column that has data in it. So again, the matrix can either be numeric, logical, or character. It can't be a combination. It has to be just one. So if we question mark matrix, the main three areas that you need is the input data, the number of rows, and the number of columns of the matrix. So we're going to simulate some input data. So we're going to create a sequence of data from 2 to 100 by 2. So not 1 through 100. It's going to be in combinations of 2s or in sequence of 2s. We're then going to make a matrix. We're assigning this matrix using the function matrix. So we're going to fill the matrix with these numbers we just created with x. And we know that there's 50 numbers here. So we want 5 rows and we want 10 columns, and which adds up to 50. So it'll fill it in completely. And again, we have the parentheses on the outside just so it will print right away and you guys can see what's happening. So this is what happens. We have 5 rows, 10 columns. And as you can see, this data, as it fills in through the vector, it's going to fill from 1. It's going to fill the columns in order from top to bottom. Now, if you're like me, I like it to fill in the rows and go across because generally my data sets are designed in rows. You can do that by including the argument by row equals true. And if we run that, we can now see that it goes across the rows to continue. So it just depends on your data and how you want to fill things in. If you already have like a square matrix, you can also load it in, and we'll talk about that later. But just remember these functions like as dot matrix. You can do stuff like this and convert something into a matrix. Now you might have to play with that if you have character vectors, you have to fix them before you do that, but things like this are easily used. Matrix. We can also ask the class of this, and now we're going to get back a matrix / array because they're the same thing. A matrix is just an array with one dimension on the third dimension. Okay, so we're going to talk about recycling again because it's important if you're simulating data and you're filling a matrix with random data. So for example, what if we only have 3 rows instead of 5? So we only have 30 cells, but we're putting 50 data points in. What's going to happen is it's going to give you a warning. It's going to say you don't have enough rows, but it's essentially telling you it's stopped. So you didn't get all the way through the vector. You only filled 30 positions and you left out 20. This is fine as long as it's what your objective is, but you have to keep that in mind that it will stop prematurely. It will not add more rows to the matrix. You can also see here that if we go to 7, so more than we need, it will continue and start filling from the beginning of the vector over again. So it'll start recycling. So that's something that you have to keep in mind if you're going to make matrices, is that you don't add too much data. It will not add NAs after the vector ends. So you could always go back and fill in with NAs using subsetting and assignment, but it's always better to try to use data that's square. And if you need NAs in there, you should have them in your vector before you fill the matrix. Okay, so that's essentially a matrix, and it works the same. It's essentially a bunch of vectors together, but filled in whichever direction you tell it to, which gives them all their unique spot in an XY coordinate rather than just an X. Okay, so we can subset these as well, but now we have 2 dimensions. So instead of just having the 1 in here, we have to do a comma and put the Y dimension. So this would be what's called the I, and this is the J dimension, or you can refer to this as X and Y. So I want to take the matrix position at 1 and 7, so it should return 14. So that's the value at cell row 1, column 7. We can also so the comma is separating the I and the J, but we can take multiples. So you can say I want rows 1 and 2, and I want columns 2 and 3, and it's going to return a subset matrix of those values. So this is a new smaller matrix. We can also ask for specific rows and keep all the columns, or ask for specific columns and keep all the rows. So it depends on, for example, in this one, if you want just rows 2 and 3, but you want all of the columns, you leave the information blank after the comma. If you want all of the rows and some columns, you just reverse it on the side of the commas. And if we run this, this is the output. We have all of the columns and only rows 2 and 3. You can also use negative numbers when subsetting. So that means delete these and keep the rest. So I want to throw away rows 1 and 2 and keep all the columns and then keep all the other rows. So if we do that, and the negative has to be outside of the vector of the rows you want. We now see we have this subset, and since we start at 42, we've deleted those earlier rows from the matrix. So you can do very simple things to cut and paste if you need to pull stuff. And then you can also, remember it's still a vector that's just being assigned to cells. So you can subset as a vector. I would not recommend you do this, but you still can. You can say, give me the first 10 values from the matrix. So it's going to do that, but it's going to do it by the default, which means by column. So if we look at that, and then we look at 1 through 10, if we want to pull 1 through 10, it's going down the columns, right? Because 4 is here. So you have to remember that if you're going to pull stuff like that, you should probably fill your matrix that way if that's how you're going to work it. And then if you want, position 1, 3, and 5, you can do that. So you'll get 2, 42, 82. Okay. You can also use logical vectors to assign which positions to pull out. So you can say, you have 5 rows, so you can say true, true, false, false, and then which is going to pull the 2 first rows, 2 first columns, and throw the rest away. So these are all options on how you can subset. You can also assign names in the matrices. So it's a little different. It's not names. You have to assign row names and column names. And for example, here, we're just going to do R1 through 5 for the rows and C1 through 10 for the columns. And we can assign those. And if we look at this, we now have these names, which makes it kind of nice to follow. So this can be nice before you're subsetting, because when you subset, the names are maintained. And you can then use the names to subset. So you can say, I want all the rows and give me columns C5 and C7 as characters because they're names. And if we do that, see how we've maintained the names now, and I've also maintained C5 and C7. And I'll show you why this is nice, because if we just put 5 and 7 here, oh, sorry, I'd have to remake the matrix. Let me remake it really quick just to show you guys, because it's okay. So we're going back to this. So for an example, if we use this value here with the names, we can then see we still know that was 5 and 7 from the original. But if we just used 5 and 7 and we didn't have names, we're going to get, it's all going to revert back to 1, 2, right? It's not 5, 7 anymore. It's 1, 2 now. It's become a new matrix. But if you want to still remember that it's 5 and 7, or that it's, for example, height and flowering time, changing these names can help with that. Right? So now that I've added the row name, I just added the row names back on. I can, if I do 5 and 7, it still comes back with the names because I've added names. You can also transpose a matrix, which means you flip it basically 90 degrees. And this can be important if, again, if you're doing like principal component analysis or something on those points where you need to, like, if it reads columns as the data, but you need your rows to be the columns, you can just shift it with this transpose function. So I'm going to print just mat so you can see it. So we have 5 rows and 10 columns. And if we transpose with T, we now have the names stay the same, but they've become the rows. So we have 10 rows and 5 columns. We can also change the dimensions of the data, because remember, it's all still in a vector in theory. So this has to be the size of your matrix. If it doesn't work, it'll give you an error. But we can change this matrix to a 2-row by 25 column matrix by saying dimension matrix that we have, because this is our matrix, and we want it to be 2 rows and 25 columns. When we do that, nothing prints, but if we run mat again, we now have this matrix that has changed. So you can do that if you need to change it to do, for example, linear algebra or matrix algebra, and it's not in the right format. You can do things like that. And we're not going to talk about matrix algebra in here, but I think it's pretty easy to find, but it's like a percent times percent or something you can do. But there's some code kind of like this, and you can do matrix algebra. So that's how you would do that. And look that up if that's something you'd like to do. A lot of the advanced multivariate analysis and GWAS and mixed modeling uses matrix algebra in the background to estimate these variables. Okay, so we're gonna just, this is gonna be quick. An array is just a matrix with a third, it's matrices stacked on top of each other, essentially. So if you ever look at a hyperspectral cube, it's basically an array. They call it an array. It's just the exact same X by Y, and there's just different dimensions of wavelengths, right? So you can do the same thing with an array, and you can simulate things like that, or you can save data like that. So an array, you're going to put your data, and for this, we're just going to use the numbers 1 through 24. And then you're going to have I, J, so rows, columns, and then the number of, I guess you would call Z's. So the wavelengths of the hyperspectral cube is the best example I can give you. And if you build one of those, you then see that you have matrix and another matrix, and it's just filling the numbers in. It's going to continue, and it will recycle as well. But you have this third dimension up here, which is your first array and your second array. And you can do the same kind of subsetting. Like if you just want the second one, you would leave I and J blank, and you'd say, give me 2. And then you have array 2, which is the same as this, which is nice because they label it. And arrays can be as many dimensions as you want. So you can go to whatever would be after the Z dimension and add 2 more dimensions. And if we run this, we can see it's a lot bigger, but we have the same thing. We have a 3 by 4 array, matrix. Then we have it always goes by the farthest dimension. So this is the first, but within the first, we have 3 of those. So 1, 2, and 3. And then we go into the second of the fourth dimension, and we have 1, 2, and 3 matrices of the third dimension. So that's as far as I'm going to go with that. I don't really use arrays much anymore. They're good for simulations sometimes, but I don't use them much in my work, so I don't have a lot to say on those except how they work. They're good for simulation data, though. We used those when I learned. We used arrays to simulate populations. So like one dimension of the array could be a population, the next dimension of the array could be the environment, etc. And then the XY is like individuals and genotype calls or something like that. Okay, so this is all gonna wrap up to data frames, and basically data frames are what's called they're a special list. And what a list is a list is like a form of data in R where you can have whatever you want inside of a list. So a list has as many subcategories as it needs, and each one of those can be a different form of data. So it can be numeric, and then the next one can be character, and the next one can be logic, but they're all within the list. But the thing with the data frame is it's a list, but everything has to be the same length. So in an old-fashioned list, you could have like operator 1 can be 300 length, and the other one can be 600, and the other one can be a single value. In a data frame, it has to be all the same length because it's essentially an Excel sheet. But every column can now be numeric, it can be categorical, it can be a factor. So it's like if you ever use jump, you're basically working with a data frame in jump. Or SAS, when you put things into SAS or something like that, those are essentially data frames because you can give them each column can be its own unique data type. So if we're gonna just make a data frame the old-fashioned way, using some of the functions that we've learned today. So we're just gonna make by doing data frame, and then in parentheses, by doing genotype equals, what that's doing is it's saying make a column with the name genotype, the label genotype, and then within it, let's make this maze 1 through 20, just as in the genotype names. And we're going to repeat that 3 times because we're going to basically make an experimental design really quick. Comma, replication equals, and we're going to replicate 1 through the number 1 20 times. We're going to replicate the number 2 20 times. Sorry. And we're going to replicate the number 3 20 times. And then we're going to bind them all together into a vector in that order, just like this. Need one more here. So 21s, 22s, 23s. And then this one, just to show you, sorry, is like this, maze 1 through 20, and start over, maze 1 through 20. This is so the genotype can meet up to the reps. And then we're going to use random numbers to simulate height data from 1.5 to 3 meters. I like to say string as factors equals false. So you can always change to factors later, but it's nice to not have R try to decide if things are factors or not. It causes more headaches than help, in my opinion. So if we execute that and we look at this data, we now have a genotype column, a rep column, and a height column. And all the data has been put into those. We can use these things such as n row and n column are very popular, and I use them all the time to check the data. So there's 60 rows, there's 3 columns. We can do structure, str of the data, and it's going to tell us it's a data frame. There's 60 total observations with 3 variables, and it's going to list the variables, genotype, rep, height. It's also going to tell you that the genotype variable is a character, and the other two are numeric variables. So we have multiple data types in a data frame. If we go over here in our environment, we can also see that data is here that we built. And if we click this little down arrow, we get the same information that's in structure. So when we're in RStudio, we don't necessarily have to use the structure command if we don't want to. You can also use the summary data, the summary, and it will give us summary information for specifically the numeric information of the data set. And it will tell us that genotype has a length and a class, and that's about it for character. As we kind of hit on this before, if we use view and with a capital V and then data, this is much nicer in RStudio than looking at the data like this. This is not easily to interpret. If we use view, we can open up another screen, and it looks kind of like Excel. It's not interactive, but it's much easier to, work through and see multiple columns when we need to. And almost everything that I work in nowadays, I've tried to be in data frame format, especially because, like we were talking earlier, tidyverse and dplyr and tidydata, it's all based on data frames. So, and also ggplot and all of these really nice packages that a lot of people love to use are all data frame based packages. Okay, so as we saw in the structure data, there's these dollar signs, which are how you can pull data from your data frame. So if I say $, I'm going to put this up here for you guys just to show you. If I say data $genotype, I'm asking it just give me the genotype column, and it'll just print out what we built earlier. Some of the things you need to do when you're doing analysis is sometimes you want things as categorical data rather than character data. So there's a difference. Like in character data, they don't group, but in categorical data, they group. So you have to change them to factors to group things. And this can easily be done by as factor. So you say data $genotype, assign this as you're basically just transforming the data to factor. And if we look at data genotype again, we now have the same data, nothing's new, but we have this new thing that's the levels, and these are the groupings. So if you plot something like a categorical plot and you code it correctly, which we'll talk about in an advanced course and plotting and things like that, and also in your statistical models, things have to be in factors to group correctly. They can't just be characters. They need to be known that maze 1, all of them should be grouped together and treated the same. Again, if you're doing something like a experimental design, you would want to do the same thing for like the rep, because the rep should be grouped. All the ones should be assigned their own variance compared to 2, compared to 3. So you can do that as well, same thing. And if we look at rep, we now have levels 1 through 3. Okay, so that's a quick introduction to factors. It's not that complicated. We'll go into a little bit more about it in a minute. That's just why you would use factors and need to transition your data. So if we say structure data now, we now have factors and they print the levels. Factors that print the levels and still numeric. So we transformed the data to the data types we need. We can still subset the same way we've been subsetting a matrice. We can say data, give me rows 1 to 20, and then all of the columns. And then that's what you get out, 1 through 20, and you keep all the columns. So you can still do that. You can also start using your logical operators to do things. So you can subset out. So what I'm saying here is subset the data, and in the rows, I'm saying look at column rep and give me all of the rows where column rep is equal to 1. So I'm pulling rep 1 out. And that's what we do here with the $ rep. You could also change this to, if you memorized your columns, you could do, I'll just do it below, but let's show you guys here. So we can pull that, and now we have rep 1. All of it comes out, right? Looks great. This can be done a more old school way where you do a subset within a subset, right? So saying, look, this is the same thing, and it's going to give you the same data. So it just depends on how you want to learn it. I don't do this because I don't remember what all my columns mean. And like anything else, if you start writing $, RStudio will tell you what your column names are, and you can just go down, pick one, and press enter. Okay, so we can do the same thing for the genotypes and using a character, because genotypes are a factor, and factors have to be searched as characters sometimes, especially when they're more of a character type than numeric. Even though rep is a factor, it's a numeric factor, but genotype is a character factor. So we can do the same thing. Pull the data for entry 5, genotype 5, all the columns. And so we can get our information for that. There's all 3 reps and the heights, and we can move on if we need to do something with that data. We can also do something like give us all of the observations where the heights are less than or equal to 2. Run that. Everything is less than or equal to 2, and we get all the columns. So we can also order our data frames by using the question mark order. And by using that within the row of the subset, it will reorganize the data frame to whatever you want. So in order, you put in what you want to use to order. So for here, I'm saying reorganize all the rows so that they are from shortest to tallest in height, and keep all of the columns. And we can see that now that as we go up, the heights get shorter and shorter. You can also do, I think it's decreasing. Yeah, decreasing equals true, and then it will flip it, right? So now we have the lowest at the bottom and the highest at the top. Okay, so what if we want to order by a factor, by the genotype? It's a factor now, it's not a character. So let's just try that, order by genotype. All right, that's weird. Why are we going from 1 to 10? So anyone that's worked with categorical data knows that it's just based on what comes next in the sequence. So since this has got a 1, 0, it's going to come after 1 instead of 2. And this is more complicated to fix. The easiest way to fix this would have been to have numbers that said Maze 01, Maze 02, and that saves some time if you have the foresight to do that. But sometimes that's not the case when you're working with data and you have to fix it on the fly. So if we look at this again, the reason is because if we look at the data genotype, this is the ordering, this bottom row of the levels. And we have to tell R to reorder those. And we can put them in whatever order we want. So we can say levels of the genotype, and that's the order they're in. And that's how we see the ordering come out. And we can use this. So this is, I had to look this up, honestly, when I first learned how to do this. We can assign them a new order, data $genotype, assign, then you say, make a factor of the data genotype, and then you tell it the levels, but you order the levels with your brackets, right? And I had to do this manually because that's just how you might have to do it sometimes. So we go from 1, and then maze 2 is in the 12th position, and you put them in order that you would want them. And this becomes really handy when you're graphing. And if you execute that, and you didn't do levels, again, now we're in order. So we can use these techniques to rearrange our data and make them look the way we want them. If we want to, we can also like reorder them based on like the means. So we can look up the means and then order everything based on which one has the highest mean to the lowest mean to make our graph really look nice and go from ascending to descending, things like that. That's where I use this a lot. Okay, so then we can do the same thing now because our data is still, the old school data is not ordered. It's still just ordered by rep. We can now order by genotype because we've changed in line 704, we've set the new order of the factor. And if we do that, we now see that each genotype is in order from 1 to 10, to 20. So those are really, cool things you can do to make your data clean and really much easier to interpret. So in this case, it's ordering by maze and then by the rep number, but we can also do double orders where we might want to order by the genotype, but then put the highest value first. So you just would do a comma within the order, and that would give you height as the second. So if you ever do like custom sort in Excel, this is doing the same thing. You put it in hierarchical order of how you want to sort. And if we run that, we can now see, for example, on 20, the second rep is the shortest, the first rep is the middle one, and the third rep is the tallest. So it's ordered it from lowest to highest. Okay. So are these functions that are called column bind and row bind? It's called cbind and rbind. And you can add things to your data frames. You can also add rows and columns to matrices. The thing with data frames, though, is that so when you cbind, you say what is it you're binding together? You're binding the data frame that we've built, data, but we're going to add another column to it. So we have to make that equal. So we know that there's 60 observations in the data frame. So we're going to make a flowering time column. Flowering time FLW equals random numbers, 60 of them from 55 to 70. And we're going to bind that to the end as the next column of the data frame. So if we look at data now, we now have this new flower column. So we can add columns. We can also add rows. We just have to make sure. Okay, so here's another example. We can add male, female as sex. But this example shows that as long as you have 60, you don't have to do it like with the cbind. You can just define a new name by doing $sex. And then as long as you make 60, it knows that you want another column added. So we've just added, okay, sorry. So I forgot an argument here. So I have to, that's what it's saying, cannot sample larger because I need to set replacement to true. So I did that. And then if I do that now, it worked. So if we look at data, we now added a sex column. And by doing that, by just doing data $sex and assigning it these values. So there's multiple ways, again, to do these steps. This is much easier, in my opinion, for this. When it comes to adding rows, you have to ensure that you have to make essentially a new data frame within rbind, and then use the same names. And if you don't use the same names, you'll probably run into errors. So we're doing the same thing. We're adding a new data frame below our data frame. Maze 21, 3 reps, simulating 3 height data, and we're simulating 3 flowering data because we've added flowering on. We've also added sex, so this actually won't work right now because I don't have the sex variable in it. So see, it does not match up. what we need to add is sex equals C male, male, female. Okay, so we've added that, and now this will work. And if we look at it now, we have a new row at the bottom where we've added that data in. So if you bring in like two data sets that are, for example, phenotyping data sets that have the same columns, you just want to stack them on top of each other, you can use rbind and just stack a bunch of things on top of each other. Okay, I think we're going to finish. We're almost there. So any questions before everything we're going to do? We're done with data types and data structure, and we're going to move on to some logical looping just to get an intro to it. So if there's any questions on data frames, matrices, let's ask those now. If not, we're going to move on. Hey, Sarah. Yeah. Okay. So good question. Sarah's asking, why did I put male twice? Okay. So that's a good question. So R can assume things. If I did this correctly, I should have actually put rep this 3 times, but it's assuming that I just want it to fill with maze all 3 times, maze 21. But it's because I added 3 rows. So I have to add 3 sets of data. It could have been female, male, female. It's just whatever you need it to be. So it just needs to be, because we're adding all 3 reps. So we need to add 3 height estimates and 3 flower estimates, and then 3 sex identification for the data to work. So I can show you what that looks like if we just build this. So this is what we built, and we're just kind of attaching it to the bottom, but it has to be the same for that to work. It has to be the same amount of columns with the same names. So attaching data frames below each other is a little bit more complicated than attaching columns. But once you learn how to do it, it's really not that bad. And this is you do this a lot if you're like looping through things and you're like building a data set line by line. This is how you kind of have to do it sometimes. Okay, so we're gonna kind of do something. So thinking about, we've just made this data set, we've built it, we want to save it, right? We don't want to have to execute this code all again. So this is all dependent on your working directory, and that's where things are saved. So if you press git, if you do git working directory, it's going to tell you where you're at right now. So I'm in my desktop of my user, and if I go to my files, that's where I am, and over here on the right. You can set that to wherever you want. For example, I want to go to the downloads of my desktop. I would set this, and you're gonna have to change this to however your computer is set up. And I like to use the double /. Either the one backslash or one / won't work, so I always use double /. It's just the method I like to use. But for the purposes of today, we're gonna do it the lazy way. So there are lazy coding. The reason I don't recommend this in the future is because if you ever go back to your code later and wonder where the heck was that file, if you don't have the whole thing written out, you're going to spend hours looking for it. But for today, we can use this choose dir inside of setwd, and you can pick whatever you guys want to pick. Okay, so like I'm going to pick downloads for now. And now if I go to my working directory, it says that I'm in my downloads. Or if I do it this way, so I some things, I think this is just the wrong path. If I do this and I go back to the working directory, I'm back in my desktop. So we're going to save this data frame by using this write.csv function. The first step is you tell it what you're saving. So the data, comma, where do you want to save it? So if you set your working directory, you don't have to put the full path. You can just put the name of the file. You have to put the .csv at the end, or the .tab, or whatever you want it to save as, or else it will not save correctly. I always write the full path because I always want to know exactly where it was put. Even if I change the directory, I always write the full path. I don't ever, unless I'm like getting into a really advanced script where I'm changing paths a lot. I say row names equals false because we don't want it to save these numbers as a column, 17, 37, 57. It's not really useful. And I also like to use quote equals false just so things aren't in quotes if I open it in Excel. Just things you learn along the way after you do this a lot. So you guys are welcome to, this isn't going to work for you guys because you're not in this directory, but you can execute this one and see that if you write this, okay, I don't know where it is, but if I save this here, it's going to save it where I had my working directory. Right, so it's saving in my desktop. And it's saved right here, maze trial examples. So if you set your working directory, it will save there without having to put the whole path in. But again, I wouldn't encourage you to do that. And we'll just open this really quick so you guys can see. We have what we built. Now you can open it right up in Excel. Okay, so we're gonna remove it just so it's not over here. And we're gonna show you how to load it back in. So you can do read.csv, the full path for me, or you can, since we're still in the same working directory, you could just do this. It's going to find it because it knows to like look in the directory you're already in. Header equals true to save the first line as your column heads. And then again, string factor equals false. And if we do that, the data will reopen, as we can see here with the view. The dimensions 63 by 5, like we saved them. And the only thing is the structure has reverted to character and integer because we said do not string as factors. So if you do this, you'll have to go back and like reassign factor names if you need to. Just remember that. Okay. If you, for example, want to open an XLSX file, you might have to use an additional package or something. So I don't execute this code. It might slow everything down. But you have to use the function install packages and in quotes, whatever package you need, and it will install. And once it installs, I'll show you on my end. Once it installs, you'll get the arrow back. But that doesn't mean you can use it. You have to actually call it in and load it into the R environment by using the library function. So once it comes in, then you can now use the functions within the package. So that's just a quick tip on that. We're not going to go into that today, but we'll go into that in detail and when we use advanced packages and other workshops. That's just how you would do it. And again, here, like we were talking at the beginning, this was not built at the most current function. So you may run into errors or warnings, and you may have to revert to whatever the last or most the last up-to-date version for readxl would have been. It's most likely going to work fine, but if you have issues, reverting back is usually the best option. Okay, so we're gonna try to get through this just so you guys can get an introduction. This is probably the most difficult part of everything we talked about today. Conditional statements. So if statements is the first thing we're talking about. We're going to set a seed, and we're going to make some random numbers so we all have the same numbers. So we're going to make one random number, actually, just for the purposes of this. so -3. So we made one random number between 0 and 10, and we rounded to 0. And we rounded to a whole number. So this is how an if statement works. It uses logical statements in parentheses to define if the command within the curly brackets should be performed. If the statement within the parentheses is false, the command within the curly brackets will not be executed. So if parentheses, the random number is less than, I don't know why that was t, but we're going to put 0. It should be 0. If the random number is less than 0, execute this print function. So here are the curly brackets, and you can do this on multiple lines because you could have like another code and another code and another code, and it'll do all of the things in the curly brackets if it's true. You could have a whole nother script in the curly brackets to execute. So and then you have to close the curly bracket, and that could be up here. This is the way I like to code to keep track of everything. So if we execute this, it printed 3 as a negative number because if -3 is less than 0. And this can be a much more complicated question. It's just a very simple example that whatever is in here, if it's true, it will execute whatever is within the curly brackets. We can expand upon that by adding an else statement, which means if it's false, it's going to do something else. And you don't have to add a whole nother statement of rand number equals, okay, let's ignore this. So ignore that test set to false. So if rand number is less than 0, I had to change that again. Sorry, it didn't save that. If it's a negative number, print is a negative number, else print is a positive number. So for the sake of this, let's set rand to 7 so you can see. So it's a positive number now. Or actually, let's just run it first and we'll see. It's still going to say that. If we say rand number is 7, so it's a positive number now, and we go back up and run this, it now says rand is a positive number. So remember that if you have rand number is -3, right? And you run this in order, it's going to say -3, and then if you run R works down. It works logically. So whatever you tell it, the next thing it does. So your script has to work that way too. We're able to do this because we're jumping back and forth. So since we've set this to 7, now we can jump back up and run it again, and it will come back as positive. If you're running this as a real script, you would want to have this below it to test again. So rand number equals 3, test, yes, -3 is a negative number. Rand number is equal to 7, test. Rand 7 is a positive number. So you have to keep it chronological like that. You can't like run it and then expect R to know to go back and do the test again. Okay, so you can also do if-else statements. So which means you can have more than one else statement, but what that means, and we're just going to show a quick example of x equals 0. So your original statement is x is less than 0, print a negative number. If x is greater than 0, it's a positive number. Else, if it's false for both of these, it's going to say print 0, and it doesn't have to do a logical test. So R works these in order again. So it's going to do x is less than 0 first and test that before it moves on to the next one. So think about this when you're writing script. Whatever is the most common true answer in your if should always be your first question, your first logical question. Because if you don't, you're going to waste computational time asking this question, followed by this question, and then finally getting this answer. Whereas if you just put x equals 0 as the first one, and 90% of your script is that answer, you're going to save all these extra steps every time. So your most complicated, least true logical statement should always be your last one. Okay. And you can stack these. You can have as many if else's as you want. You could have 300 of them if you really wanted to. So we're going to do one other if else. So there's a difference. This is else if. I'm sorry, I said that wrong. This is an if with an else if. There's also a function called if else, that if we, again, make some random numbers, like we see here, did not find function. Oh, I wrote that backwards, so that's why it didn't work. Okay, so if we set seed instead of seed set, and then we make some random numbers, so we're asking if else. So we're doing even or odds. So we're doing that thing again to see if there's a modulus, to see if there is a remainder. So divide the numbers by a 2, and if the remainders are equal to 0, it's an even number. And if they're not equal to 0, it's an odd number. And those are the two options. So if you use like an if in Excel, this is basically an if question in Excel as well, but they call it if else here. So if we run that, odd, odd, even, odd. So odd, odd, even, odd, odd. So it achieves what we were asking it to do. Okay, any questions before we hit the last couple of things quickly? Okay, I'm sorry we're going a little bit quick at this, but when we do a more advanced course, we'll spend more time going over these again. Okay, so a loop, which I use a lot in my research, is an iterative cycling of code. So it iterates through a sequence of a vector and applies those values to multiple lines of command code that are executed in the curly brackets. So this is an example for some value in a sequence or vector. So it's going to go through each location in that vector, execute the statement. So for example, if we were doing, let's find out how many even numbers there are in the test numbers vector that we just had, this one. We can do it simply with the sum and doing the test, because the ones are true and those are how you would, it just adds up the true values, and so we have 3 even numbers. We can make a variable called count. So we're showing different ways you could do this, and obviously you would want to use this. It's much quicker, but to show the purposes of a loop, we're setting count to 0. So for value, which is what's called a soft code, it can be changed. You're gonna iterate through the test numbers. So it's going to assign value each one of these numbers until it gets to the end. So for the first loop, it's going to be 73. For the second loop, value is going to become 57. For the third loop, it's going to become 46. And you're going to do the test. And so this is an if statement, and we have the loop is here. This is the val and sequences, and this is where what we do inside the loop is these 2 brackets. But within the loop, we put an if statement, and within that, that's what we execute. So you don't need an if statement. You could just loop through and say value plus 1, value plus 2, value plus 3, and it would do that. But we're going to count here. So every time this value is true, that it's even, we're going to add a 1 to the count. So it's going to keep summing up. So this is going to go really quickly. And then if we just print count, we get 3 again. So it worked through it. It's a lot more coding, but imagine if it wasn't as simple as just the modulus. So for example, we could do print val plus 1. So if we run this code again, it's going to, every time it goes through the loop, it's going to print, because it's looping through and doing the same thing. So it's doing 73 plus 1, 57 plus 1, 47 plus 1, and it's printing that out every time because that's what we told it to do. Instead of previously, what we told it to do was assign count. So you can assign factors in here as well. And I don't want to get into the weeds on this because it could take, you can get very, very complicated loops. So we can exaggerate this a little bit more and make it a little bit more complex, make a matrix full of zeros. And here's what the matrix looks like. All zeros, 10 to 10. Yeah, when it's out, it'll probably be published on the Facebook page or sent out. Yep. It's probably going to be on the NAPB YouTube channel. So we have that matrix, and what we're going to do here is this is essentially I and J we're making these variables up. So we're going from 1 to the number of rows in the matrix, right? So there's 10. So we're looping through all of these 1 through 10. So we're going to start with 1, and we're going to keep 1 constant until we get through all the J's. So this is a loop inside of a loop. So for the J's, we're also going to loop 1 through 10, but it's going to accomplish the J's first. So it's going to stay on 1 for I, and it's going to go J1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and do the test. And then it's going to go to 2, and it's going to do all the J's again. So that's how it loops through. There's hierarchy in the loop as well. You have to complete the inner loop before you can go to the next step of the outer loop. And in here, we're asking a simple question. If I is equal to J, it's a diagonal cell, and we want all the diagonals. And if it is equal to J, we're going to set that location, ij, equal to 1. So when I equals 1 and J equals 1, it's going to become 1. And if we do that, and then we print mat like this, we now see that all the diagonals are now a 1 because it's tested that and looped through it and changed all of those things. So you can start thinking about how you can start doing these kinds of things to work through your data. Okay, 3 simple quick ones. I don't use this much, but it's a while loop. It's essentially the same thing. You have to set an I value. For example, 1. We're going to set I to 1. And you're going to say, while I is less than 20, do what's in here. So you're going to just print I. But the thing with a while loop is, if you don't adjust the value, it will go on for eternity. So if I do not add a 1, or if I subtract a 1, it's just going to print and print and print and print and never stop. It will never stop until this is satisfied. So you have to make sure that you reassign I at the end of the while loop. So every time you go through the iteration, you change it to whatever it needs to be. These aren't used very common because they can be tricky, and if there's some little quirk in your code, you could just your code will run for weeks and it'll never end because of one little mistake here. But for example, we'll do it here because this is an easy one. Okay, it's printed, it's done the print I, and then it stopped because it tested it. It tests first, and if it's true, it's done. And so we don't see a 20 here because it's like, oh, I is 20, so we're stopping. If we said I is less than or equal to 20, then it will print. Oh, we have to reassign it, right? And then we can print it and it'll go all the way through. So those are just, that's a while loop, really easy. So there's 2 parts to a loop that you can also do. They're going to be assigned after we get some feedback from this first one, what we're going to discuss. Okay, so if we have, and we're a little over time, but we just have 2 more things. They're really kind of important. If you want to break the loop and just stop it cold, you can use what's called a break function. So looping through values of 1 to 10, if the value is 7, so once value gets to 7, it's going to stop the loop. So, but until then, it's going to print the value. So we can see here, it prints 1 through 6. It says, if value equals 7, break, crashes the loop, we're over, we stopped. So that can be useful if you want to just get to like a convergence factor or something, you stop. You can also do what's called a next. This is the last thing we're going to cover, where if you want to skip something, like, so if a value is NA, like if you're looping through a vector and like an NA comes up and you just want to skip it because it's NA, what you do is you do a conditional format in your loop, and you say a conditional statement, and if it equals 7, it's going to skip. So we can see the difference here, whereas we print, oh, it hit 7, don't print, because we skipped to the next loop. We skipped, we said next. Yep, sure thing, Nate. So if that's what's happening here, is it's going to continue the loop, but it's going to, when it says next, it's going to say, okay, don't do whatever's below next, go back and jump to the next value of X in the loop. And I actually use this a lot in my coding. I don't use break much, but I use next a lot. I really like using next. Okay, we're a few minutes over. I'm actually really happy we made it through everything. A little bit of it, I hope that all of this kind of gave you guys a really good intro of what's possible and kind of how to think things through. Again, the one thing I want to say is that nothing in R is only achieved one way. You kind of have to figure out your way to write, and eventually you'll learn how to improve that. You'll learn how to streamline things. I still learn all the time, and we'll see in future workshops. I think there is one already planned, how you can use some of these advanced packages like dplyr and Tibble to make your subsetting and your data manipulation even easier than this old school way of doing it. But understanding how it works in the background is really important. So I hope you can think about that if you attend these future workshops. What would you want to skip in the iteration? Are you talking for the next statement, Chris? Yeah, so it's like, okay, so I'll do it here. Right, so let's do something like this. Let's assign that. And instead here we say is.na. Right? It should be fine. Yeah, one more. Okay, so what we're doing now is we're going to loop through the values, and if it's an NA, we're not, instead here, let's do like print value plus 10, right? So if we do this, we're only going, so we don't get NAs. If we exclude this, right? I'm just going to comment it out and run it again. It's going to do this, and we'll still have NAs in our data, right? So it's an easy way to skip by that if you want to just get rid of the NAs. It just depends on what you're doing. So if you're building another variable and you want to keep the NA there for consistency, I wouldn't use the next. I would use the next for something that you're trying to subset down to smaller numbers. Got it. I was wondering how to reference out properly. Okay, cool. Awesome. Any other questions?
All right, we'll give one more round of questions and then we can call it.
Yep, if there's anything else, and I'm sorry that a little bit of the code got moved on the fly. I hope you guys caught it. If not, you can be able to follow the YouTube to see where we changed some things.
This was excellent, Steve. Thank you so much. You were so patient and you'd put in so much effort to make this workshop work out for everybody.
No, you're welcome. Yeah, I think it was really good. I'm glad we got through all the material. I think this is like a point, like if you can grasp this, it makes everything so much easier. When I had to learn all this myself without anyone explaining it and using the internet alone, it was a lot more complicated. But I got to say that I've been writing R for 5 or 6 years, so I've been doing it for a while now, and it takes time. It's like learning a new language. Just be patient. Don't get too frustrated with it. Reach out to people that can maybe help with an easy solution.
All right, we'll send you out a survey out to everybody. If you would like to give us feedback on some of what we did today and what you'd like to see in the future, that would be great. So please keep an eye out for your emails. I want to say thanks to Steve and everybody else for attending. And with that, I'll end this meeting. Does it sound good, Steve?
Yep, sounds good. I think I gave you the hosts back.
Yes, sir. You have a nice rest of the evening and
all right. Have a great holiday, everyone.
everybody.